Sorry, I'm not going to be able to see you in class today. I only had one example to walk through that sort of acts like a springboard for the rest of this week. Now, your instructions for weekly assignments are posted to Schoology. The objective is to complete the video or watch the video notes that I posted to Schoology for Unit 2, Part 1, and that contains lessons 1 through 4 for this week, for Monday through Thursday, essentially. So watch those videos that I posted online and complete the worksheets that go along with them. A printed copy was left behind for you today. There's also a PDF copy online as well. But take a picture of those when you're finished with them this week and send them back to me with that assignment, and we'll do that again for next week. That's how you'll get credit for your video work in this unit. For Math Excel, there are 3 Math Excel assignments out there, so please make sure that you're starting on them. I believe they're labeled Homework 4 up to Homework 7. This number 7 is going to act a lot like a test review, so it's going to be larger than the others, and I am going to require it. So don't wait to get started on number 7, since it is one of the bigger ones. Make sure that you get to a point where you're starting that with more than a week to spare. All of these assignments, the videos and Math Excel, are going to be due on October 11th, and that's the Sunday before our next test. And our next test is October 16th. Now you'll notice that this is called Unit 2 and 3, and that's because the test itself usually goes into the gradebook as test number 3. Test number 2 is going to be the derivative packet that I release next week. And so there's a take-home derivative packet that I ask for you to complete on your own after we've learned all of the rules. It gives you a chance to practice, and it further solidifies, hopefully, your understanding of what a derivative is and how we can use them. So anyway, that's essentially a take-home test, and I'll expect that to be completed by the 16th. That packet won't be due by the 11th, but the packet will be due by the 16th, the same day that our actual test is going to be. So with that being said, we can get on with this example. Now on your handout it says that a rock is being launched, but if you talk to any of my former calculus students or any of the students that I had this morning already, you'll know that I changed this problem to represent a grapefruit because of my disdain for that particular piece of citrus. And as it turns out, when we launch this grapefruit in the air with some sort of contraption I built at my house, I know that the grapefruit is flung at 96 feet per second as it leaves the contraption, and it shoots upward in the air. Well, according to my friends in the physics department, the equation to represent the path of that object is represented here. Now, I say path, but I really mean just the height or position of the object after time. For whatever reason, this letter S has come to stand for position in the world of physics, and then this class as well. And we'll talk a little bit more about what the position function does for us in terms of a derivative at another time, but while position is labeled with the letter S, the letter V we'll sometimes see. Now that one's velocity. That seems to make sense. And then another function relative to this group is acceleration. And that one's labeled with, of course, with the letter A. So the only weird one in the group is the letter S. And if anybody knows the reason why we went with S instead of P for position, I'd be interested in hearing an explanation, because I honestly don't know. So what I would like to do is just talk about where this grapefruit is after we launch it in the air. And so I've labeled my graph as such. The x-axis is actually a t-axis for time, and this is a time in seconds. And we'll measure from 1 through 6 seconds. I think that would be appropriate for this example. On the y-axis, which is technically s, or s of t, represents our height or our position above ground. I forgot to mention that before. Our problem says that this is the position or the height of the object above the ground, and this is measured in feet. A good scale for this graph would be by 20s. So every other line increases by 40. So let's just take a moment and evaluate what some positions are going to be at time 0, at time 1, at time 2, then again at, time 3, time 4, time 5, and if we can fit it in over here, we'll look at time 6. So pause the video and take a moment to evaluate this function at each of these test points. Resume playback in a moment to check your work. And here we have it. The height at time 0, well, of course, the grapefruit hasn't been fired yet at time 0, so it's 0 feet above the ground. After it's released, 1 second later, it's 80 feet above the ground. Then after 2 seconds, it's 120 feet above the ground. After 3 seconds, it's 144. Then it only has a height of 120 after 4 seconds, then back to 80, and then back to 0 after 6 seconds. So as you might guess, this object goes up, the grapefruit goes up, and then comes back down. And if I were to plot each of these coordinates on my graph here, we can kind of see the trajectory of this grapefruit. And my apologies, I misread my calculator. The height at 2 seconds and at 4 seconds is 128 feet, not 120. So that changes the shape of the graph just a little bit, but overall the shape is what most of us would have expected. The function itself was a quadratic function with respect to t, and quadratic functions, of course, create parabolas. We had a negative leading coefficient and a degree of 2, so we know that it's a downward facing parabola. And this graph here represents the height of that object over time. Now, at time 3, we reached our peak here, and if you can imagine, something interesting occurs. This grapefruit went from moving upward in the air to moving downward, and right precisely at this position, it switches from moving up to moving down, and at that split second, at that very precise instant, what do you notice about the speed of the object? How fast is it moving once it reaches its peak? And I'm just talking about that instant, that very split second that it's at its peak. How fast is it moving? Well, a lot of us recognize that at the 3-second mark, it's actually moving 0 miles, or I'm sorry, not miles per hour, but 0 feet per second. Its speed is 0 because it's reached its peak. It's just getting ready to start falling down, and at that split second, it has a speed of 0, or velocity of 0. Now, as it turns out, that's not a coincidence. That's directly related to the derivative function, or, as we learned last week, our difference quotient. Now, the difference quotient is used to establish derivatives moving forward from here, but we also abide by different derivative rules that we eventually just memorize so that we don't have to spend time calculating the difference quotient for each and every position. So before we get into that, I do want to point out just a couple other features of this graph. If I were to look at any of these other test points that we established a few moments ago and consider the tangent line, the slope of the tangent line at any one of those points, you should recognize something interesting there too. For example, at time 0, 1, and 2, each of these slopes are positive. Each of these slopes are positive. And so what that tells me is that this object has a positive rate of speed, or velocity. When we move over to time 4, time 5, and time 6, the slope of the tangent lines at these points are all negative, and therefore they have a negative velocity. And if you haven't picked up on it yet, I'll be explicitly clear here. The unit of our derivative, of our applied difference quotient, is the combination of our y-axis unit and the x-axis unit together. We even use a special notation to clarify the derivative, and we're going to talk a little bit more about that in another video this week. But this apostrophe, this prime notation is talking about what we call the derivative, or the resulting function after the difference quotient has been applied. And the unit, we'll get to this derivative function in just a second, but the unit is literally the combination of the y and the x values. So in this case, feet per second. So whatever rule that we establish here, the unit of that rule, or the unit of measure for that formula, is feet per second. In our original position function, our unit was simply feet. After we calculated a result, we knew that we had a number that represented feet. The results that are calculated from the derivative represent feet per second. Now, if you'd like, we could establish the derivative rule by using our difference quotient. The limit as h approaches 0 of negative 16 times t plus h squared plus 96 t plus h minus 16t squared plus 96t. We could actually go through all of the trouble of simplifying this difference quotient and then using a direct substitution to let h approach 0. That's where we were last week. Where we are this week and where we're going to be by the end of this week is that we're going to be able to skip all of that. We're going to be able to skip this entire process, and instead, for polynomials anyway, we're going to be able to look directly at this position function, and we're going to be able to pretty easily, perhaps even without any math, compute the derivative function for it. In fact, I'll give you this answer, and I'll let you think about what the rule might have been, how we can transition from position to this derivative. This rule is going to be negative 32t plus 96. So now that we have this rule, we can actually establish the speed at any position. Remember what I said a moment ago about at position 3? Well, if I didn't have a graph to look at and I evaluate the number 3 at the derivative, or in the derivative function, we would need negative 32 times 3 plus 96. Lo and behold, negative 32 times 3 is indeed negative 96. Plus 96 does equal 0, and our unit of measure, let's keep in mind, was feet per second. So this algebra here confirms that at time 3 seconds after launch, that object is moving 0 feet per second. Now you may be wondering, Mr. Ehrman, why are we so worried about this notion of a grapefruit being tossed in the air? Who cares about a grapefruit or a rock that's being tossed in the air? Well, I forgot to mention something. Because I hate grapefruit so much, my absolute disdain for grapefruit is that I want to destroy every single one that I ever see. I've learned over the years that when you throw a grapefruit into a concrete wall or a floor or some immovable object, the magic number, the magic speed, the magic velocity is 90 feet per second. 90 feet per second is the optimal grapefruit destruction velocity, or OGDV for short. What I would like to know, clearly when the grapefruit is at its highest point, it's not moving fast enough to explode if it were to hit a wall. But what's going to happen when it reaches the ground? We got a quick preview here, and we saw that at time 6, the grapefruit is going to be back on the ground. It reaches its highest point, it falls to the ground, and here at time 6, it reaches the ground. Is it moving fast enough at that point to explode? Is it moving fast enough to reach the OGDV, optimal grapefruit destruction velocity? Well, let's find out. We've got a rule that we can use. Negative 32 times 6 plus 96. Well, that would be negative 192 plus 96, and that adds up to be negative 96. And remember, our unit of measure, the combination of the y and the x-axis unit, is feet per second. So what do you think? Is it moving fast enough? Well, the number 96 looks promising, but it's a negative number. Why is it negative? Well, it's negative because the grapefruit is falling downward. It's moving in the opposite direction from where it started. And the number 96 does imply that it's moving at 96 feet per second. So this grapefruit is falling at 96 feet per second downward towards an immovable object, aka the Earth, and I would say yes, it has reached OGDV before it reaches the ground. So it is safe to say that if we put a grapefruit in this contraption to throw it in the air and let it fall to hit the ground, then yes, it will reach optimal grapefruit destruction velocity, and we will completely obliterate that grapefruit, which is a good thing. But there's a problem. I don't know too many places, and by the way, I also forgot to mention that we have to neglect air resistance here and wind changes, so it's good to do this inside of a building, say a barn or something like that. I don't know too many barns that are 144 feet tall. At least I don't have access to any that are 144 feet tall. And in order for this grapefruit to reach its maximum height and therefore have the time and distance to reach the velocity of 96 feet per second, the grapefruit does have to reach 144 feet in the air, and that's a problem. I walked outside of my classroom and I saw that that atrium behind my window is about 30 feet in the air. And so I asked myself, I wonder what would happen if I fired this grapefruit upward and strike the ceiling of that atrium. That ceiling's at about 30 feet, and I don't know exactly when that's going to happen, somewhere between the time 0 and time 1. That thing is going to reach and smack into the ceiling of the atrium. If I could find out when or how long it takes for it to reach that ceiling, I could then use this x value inside of our derivative function and compute exactly how fast that grapefruit's moving, and we can see if we'll reach we'll reach that optimal grapefruit destruction velocity against the ceiling. So what I might do to solve this, and I'm just going to separate this from our other discussion right now, is I know that the height is going to be 30 feet, and that height, 30 feet, was some s, or some position value based on this function, negative 16t squared plus 96t. If I set this equal to 0, I have negative 16t squared plus 96t minus 30, and now I could solve. There are lots of different ways to solve this. I'm going to go ahead and use the quadratic formula because I'm not sure if this is factorable. So with the quadratic formula, I've identified a, b, and c. I also calculated my discriminant, which is 7296. Out of habit, I always solve that first. That way I know what type of solutions I'll end up getting. Since 7296 is positive, I knew that there would be two solutions, or in other words, 2 times when the grapefruit in this case will be moving at 96 or 90 feet per second. Wait a minute, let me take that back. I haven't done that part yet. There are 2 times when the height of the grapefruit will be 30 feet, when it goes up and when it comes down. Now the square root of 7296 is what's going to be plugged into the quadratic formula, and that ended up being 85.41. So the opposite of b plus or minus that whole square root divided by 2a gave me 2 solutions at 0.33 and 5.67. Now this is an extraneous solution in our case because we're not interested when the grapefruit's coming down and is at a height of 30 feet. What we're interested in is how long it takes for it to reach 30 feet on the way up. So now if we take the value for t here and substitute it into our derivative rule, we should be able to tell how fast this grapefruit was moving at this time specifically. So we have negative 32 times 0.33 plus 96. And unfortunately, if that ceiling is only 30 feet in the air, it looks like the grapefruit will only be traveling at 85.4 feet per second when it strikes the ceiling. So certainly there will be some damage, but it has not reached the optimal grapefruit demolition or destruction velocity, OGDV. So we can't say that we'll optimally destroy the grapefruit, but certainly we'll do some damage to it. Anyway, I hope you found this practice problem enjoyable and you stuck with me through the entire thing. This is just kind of a preview of different ways that we can use derivatives and position functions. It's a big deal inside of science, or more specifically a physics class, but it has many other applications elsewhere too, and you'll learn to see them as well. If you've got further questions, please direct them towards me. I'll try my best to answer them as soon as I can. Otherwise, we'll catch up with each other next week. Thanks for watching.